Cardiff, and this is the title.
Okay, thank you. My title probably could equally be just part 2 of whatever Alistair's title was. I want to take what he's done and look a bit at the Frobenius algebra structure. I will mainly focus on the case of SU2, which Alistair already presented. And then I want to present a construction which is not really a higher construction, it's sort of a moving across construction, so looking at SO3, so where we take a non-simply connected Lie group now instead of SU2. But first, let me recap very quickly Alistair's the first half of Alistair's talk and present it in a way which will be more convenient for me and in a way I understand a bit better. So we can construct a modular tensor category C starting from some temporary Lie diagrams, so as Alistair described. And so this modular tensor category has simple objects F0, F1 up to Fk, where here we're taking Q to be a k plus 2th root of unity. And these simple objects are essentially Jones-Vensor projections, and they satisfy the fusion rules of SU2, which Alistair showed us. Now, a module category for this category C is essentially classified by an ADE linking diagram G, which really is telling you how the simple object F1, the fundamental generator of SU2 at level K, acts on the objects of your module category, and you can get the action of all the other objects, all the other simple objects of C from this, because, as Alistair pointed out, it satisfies the same representations, the same fusion rules as SU2 at level K, and so, for instance, we can get the action of F2 by taking G of F1 squared and then subtracting the identity, and that just follows from this fusion rule identity for F1 tensor with F1. Now, the structure of a module category can equivalently be described by this functor F, which Alistair also wrote down. For me, I will think of it as a functor from a modular category C to functors from M to M, and then we just define this. This is essentially given by this nimbrep, these graphs G, and so CAB here are just one-dimensional RR bimodules, or what Alistair had as S, I have as R, which is just the bimodule, if you like, generated by, or the vector space generated by vertices of the graph G. And then we could construct an algebra as by applying this functor F to the sum of all simple objects in your category C, and this is isomorphic to the preprojective algebra of G. For me, I want to think of G as just a graph, not as a quiver, and so my relations are the same relations that Karen wrote down for the preprojective algebra. So we divide out our path algebra by an ideal generated by sums of paths in one direction, and then you take a path in the reverse direction at a vertex, and so you sum over all of these paths of length 2, which return back to this vertex. And so there's no signs coming in here. Okay, so that's what Alistair told us. So these algebras, as we've seen already in all the talks this morning, these algebras are Frobenius algebras, and so this means that the dual algebra of A is isomorphic to A, but in particular as AA bimodules, they're isomorphic where the right action of A is twisted by some automorphism beta. So this beta is called the Nakayama automorphism. Equivalently, Frobenius algebra means that there's some non-degenerate bilinear form which satisfies the property that if we apply the bilinear form to A, B, and C, it's the same as on A and BC, as for any elements in our algebra, and you can conclude from the above that the following property. So if you interchange the order of A and B, then you introduce this Nakayama automorphism here for the second term. So to define this Nakayama automorphism, or to define this binary form, it's sufficient to define a function f, which will be defined to be 0 for all elements in the preprojective algebra of degree less than k. So as Alistair pointed out here, the grading of our preprojective algebra, every edge has grading as degree 1, and so the grading just is path length of paths on the graph G. So for anything which is not of maximal length, this function kills it, and then we choose a specific element C of longest length. We set this function to be 1 on that, and then by these relations above, f is then uniquely defined for all other elements of maximal length. And we can see that, so perhaps one note of clarification, so people who are used to operator algebras will think of a path algebra as being so tensors of paths, whereas so in this context, a path algebra is a multiplication structure just given by concatenation of paths, if that makes sense, and if the vertices don't match up, then the product is defined to be 0. In particular, all of f will evaluate as non-zero on all of these elements of longest length. So for any element of longest length, I should have defined, okay, so then bilinear form can just be defined as f applied to the path AB. So for any path of longest length, f of b is the same thing as the bilinear form applied to the source of b, so the starting vertex of the path b, and by this relation we can interchange the two, and so we have to introduce a factor of beta. And this thing, so this is then f of b beta b. And so this new path will be 0 unless the terminal vertex or the range vertex of b is the same as beta applied to the source vertex of b. And so you can read off what beta is, at least as a permutation, just from knowing what the space of longest length paths are. And what is that? Well, AK was just this functor f applied to fk, and in particular it's described by the matrix gfk, which comes from the number. Okay, so we can read off as a permutation at least how this Nakayama automorphism acts, and in fact, in the context I've described, the automorphism is just precisely the permutation. There's an awful lot of work that needs to go into finding out precisely what beta should be as an automorphism, what scalars appear in it, and Alistair, along with Brenner and Butler, looked at this, and it was essentially a case-by-case consideration of all the different linking diagrams that was needed to deduce that, and I don't know of any cleaner, more efficient way to do that. Okay. So from this, we can construct a finite resolution of A as an AA phi module. First of all, let me write down a resolution of A just as a left A module. So here, V is the phi module generated by the edges of the graph, so passive length 1. And this just comes from the fusion rules, so the nth graded part of this resolution of this exact sequence this. Alistair wrote down Alistair wrote down essentially this. We have the fusion rules that Fm, the SU2 fusion rules Fm centered with F1. We shift it by 1. Fn minus 2. And if we apply the functor f to that, that reads that the n minus 1th graded piece centered with V is the direction of the n minus 2th graded piece. The nth graded piece. You can write down very explicitly what the morphisms, what the isomorphism is. And so we get an exact sequence where, as Alistair pointed out, these terms are 0 if f of minus 1 is 0 and f of k plus 1 is 0. Okay, so this is true for all n, and so this then gives us the exact sequence that we need for the nth graded parts, because at these levels, so this is for n between 1 and k plus 1, And for these values of m, r m minus k minus 2 and r of m are all 0 because r only lives in the 0th gradient. 0 everywhere else. And so that gives us this exact sequence. For n equals 0, the mth graded piece or the 0th graded piece of this exact sequence is, everything is 0 apart from the last two terms. So it just reads as this, and A naught is precisely R, and R naught is again precisely R. So you can see that this is indeed a resolution, this is an exact sequence. A has a left A module. We can get a resolution of A as bimodules by tensoring with A. So we just tensor this resolution as left A modules by A on the right over R. The exactness of most of the sequence just follows from exactness here, but the exactness of this syzygy, this third syzygy, was shown again by Brenner but King in the almost causal paper, and the computations are essentially the same as the computation. They follow from the computations of the Nakayama automorphism on a case-by-case basis. From this, so one can get a second exact sequence if you tensor with n, which is this twisted bimodule on the right. So it's essentially just taking the same resolution and twisting the right action by beta. Then one gets another exact sequence, and they can be combined to get a projective resolution of A as an AA bimodule. So just repeating these two resolutions. So this is then a periodic resolution that Karen was talking about here with period 6, and you can use this in particular to compute the Hochschild homology of A, and cohomology, cyclic homology. These are things that Ettinghoff did with his student U. So this is the picture for SU2. There's an analogous picture from SU3, so the construction that Alistair briefly described extends. So one can compute the Nakayama automorphism again in this context. So this is something that myself and David did. And then we found a resolution of A as an A bimodule, and one can compute again the homology from this. And these SU3 algebras are really almost Calabi-Yau algebras. They seem to be basically these higher preprojective algebras. Okay. Let me now talk about the construction in the SO3 situation. And I'll be a bit more explicit about the construction of these categories. So I want to construct, in the first place, an SO3 tangent lead. So let's take Q in 4k plus 2 unity. So morally, SO3 representations only exist at even levels of SU2, but you need to take, so even level is 2k, but you need to take k to be even itself, otherwise the category that you get is not a modular tensor category. So we're going to restrict ourselves to levels of SU2, if you like, which are multiples of 4. So let me define, first of all, SO3 tangles. So these are planar diagrams in a rectangle, so one would have a fixed number of vertices along the top and along the bottom of the rectangle, and then you connect these vertices up with strings in a planar way, but one also has so planar tangles in the rectangle. But generated, so we also have a trivariate vertex. So this trivariate vertex, these strings don't have an orientation as in the SU3 case. This is more like some of the pictures that Vaughan showed us on Monday. And these are subject to relations which, again, we saw on Monday. And which are very reminiscent of the kind of pictures that Alistair showed us for SU3. So if one has embedded diagon, you can remove it to just through a string. If two strands from a trivariate vertex are attached to each other, then this just evaluates as 0, so this is a 0, not a closed string. And then the third relation that we saw was the relation of the space of tangles with 4 endpoints. This is 3-dimensional. So we have this relation where, again, these quantum integers which have appeared a few times already, like this. And we also have that enclosed loop. So this is not a 0, this is a closed string. This should evaluate quantum 3. The tangles generated by these trivariate vertices with relations here. So, an example. Something like this. This is 3 vertices at the top and 4 vertices at the bottom. And this diagram is in fact reducible, because whenever you have some enclosed face, then one can use these relations, in particular this relation between things on 4 strands, to remove that. So this will reduce down to some sum of tangles generated by this trigonal vertex, but without any closed faces in it. Okay. And so we want to consider the vector space, which is spanned by planar tangles generated by this trigonal vertex, and then with these relations. Then I want to define a tensor category called B prime. So objects of this category are projections in these tangles. So composition of tangles. So I draw my tangles the opposite way around to what Alistair drew. So mine sort of go from bottom to top. So composition of tangles here means that you stick one on top of the other and you join the strings up. So this is only defined if the number of strings matches the number of vertices at the top of the bottom triangle and the number of vertices along the bottom of the triangle above agree, otherwise it's 0. So objects are projections, and then morphisms are like tangles between projections.
Linear combination.
Yes, sorry. Linear combinations of tangles. Okay, so this is a tensor category, so the tensor structure is just given by horizontal juxtaposition of either objects or morphisms. So this is just sticking two things side by side. I want to build now matrix category, because I want to be able to take formal direct sums of these things. So matrix category of D prime, so objects are just formal direct sums of objects in D prime. Morphisms, so space of morphisms between direct sum of projections P1 to Pn. And the direct sum of projections Q1 to Qn are n by m matrices whose ijth entry is the morphism between Bi So this is essentially equivalent to the category Alistair described. TL in the context of SO3. We can define a trace of the morphisms trace on a diagram which is be given by closing up all the strands from the top around to the bottom. So in particular, this will be 0 unless the number of vertices on the top and the bottom of the morphism agree, and then you extend this to arbitrary morphisms linearly. So when you do this, you form some closed diagram, and so in particular, it will just be a collection of these closed faces, and so then you use the relations that are defined to reduce this down to a collection of closed loops, and then each of these closed loops counts as a factor of quantum 3. So that gives you the value of the trace. Then, so this category matrix, map D prime is not semi-simple, but you can quotient by so the negligible morphisms, the ideal generated by the negligible morphisms. So these are the morphisms whose trace is 0. In particular, this is the ideal generated these things are here to be. So this category C prime is now semi-simple. It has simple objects F0, which is just the number 1 with an empty diagram, F1, which is a single strand, F2, which is given by this linear combination of diagrams, and so on, all the way down to F2k. This has a description in terms of a linear combination of diagrams on 2k vertices on the top and on the bottom. Okay, so these are the SO3 analogues of the Jones-Bensel projections. They satisfy properties that if you hit any of them with a cup or a cap, or with one of these tri-rated vertices, then they're killed and they just be 0. And in particular, this ideal of negligible morphisms is generated by the morphism, which is the identity on the 2k plus 1 Jones-Bensel projection, which is the first. I'm not so confident now. Okay, so we have 2k plus 1 simple objects, and these satisfy fusion rules. So for n is not 0 and n is not 2k, the fusion rules are like this. When n is 0, fusion rules are trivial. We can encode these fusion rules in this graph. Okay. So this is essentially just the even subcategory of the SU2 temporary leap category at level 4k. But this is not the category that we want, because this is not a modular tensor category, so the S matrix is degenerate in this case, and so the answer is to take a Z2 orbifold of this, what's called fixed point resolution by Fuchs, Schelikens and Schweiger. And so I want to describe how we do that now. So what I write down where this comes from, so these two actions commute you, in this case at least, that taking this sort of even subcategory and then taking some Z2 orbifold, you could do it in the opposite direction, take a Z2 orbifold first and then take the even subcategory of that. And so Morrison, Peter and Snyder gave a scheme theoretic description of the planar algebra for D2n, in this context D4k plus 2, which is the Z2 orbifold of A4k. And so then what we need to do is take the even part of that. So to do so, to get the category that we want, so let me not. So we need an extra generator Y, which think of as this box with k vertices, k strings, k vertices on the bottom, on the top, so some generator, and this satisfies the following relations. So if we do a rotation by 1 of y, then we introduce a minus sign. If we attach a cap or a cap to y anywhere, it's killed. So, in particular, because we can, by this relation, we can rotate y. This is even true we put a cap on the end. So this relation is sort of true for these Jones-Wenzel, or these generalized Jones-Wenzel projections, but this one would not be true there. And similarly, we stick one of these tribound vertices anywhere, and that also kills y. The final relation is that if we take two of these y's together like this, then up to some quantum integer, these just give us the last simple object. So in particular, what this relation means is that in any diagram, one only has at most one y, because you can always use this relation to move the y's. You can always move the y's close enough together so that you can apply this relation. To do so, you also need there is a genuine braiding on this category, which there is. One can define a braiding via some linear combination of diagrams, which I should have done and have not written down, so I don't recall it in my head. So in Morris and Peter Snyder's original construction for D2n, there was only a partial braiding, but actually when you restrict it as even part, as even subcategory, that braiding becomes a genuine braiding. So you can hold strands, if you like, over and under one of these y boxes. Okay, so if we now do the same construction for, as we just did, but for this, with this extra generator in, and so we have a matrix category of D, where D is now projection. D has objects which are projections generated by these tangles, and we quotient out by, again, the negative morphism. Then we do get a modular tensor category. So now let me just say, so C is semi-simple, and it has simple objects naught f1 up to a minus 1. So these are precisely the same simple objects as we had in our previous category, because this y only lives in the kth space, so it doesn't affect these at all. And then in kth space we have two simple objects which are so for the other simple objects, so in particular here we have the fk. Some of these two mu. So fk, the old, which was a simple object, now is split into two simple objects, and for the other simple objects in the category without the y, these are.
Excuse me. Did you say that Q has order 4k plus 2?
Yes.
Doesn't that mean that quantum 2k plus 1 is 0?
Yes. So I went through. I always get confused whether I need to be working with k or 2k, and I went through changing things to 2k. Okay. This should not be 0. So there needs to be a small modification of that, which is possibly. You are correct. It is not 0, whatever the correct quantum integer there is. So that one is incorrect. Then we have the fusion rules. So fusion rules, at least for tensoring by f1, are given by this graph. This is just either the even part of d4k plus 2 or z2 overflowed of the graph that I previously had. So the S matrix for this category, for quadrant tensor categories, is given by Barber and Gepner, but also by Fuchs, Sheldrake and Swigert. So this is a modular tensor category, and indeed these fusion rules agree with what you get from looking at positive energy representations of the root group of SO3 by the work of Toledano and Laredo, and also Kerry-Wan that we wrote in the case of SO3. So this is our category. So next we need module categories. So module category M, in this case, will be classified by an IMREP graph G, and then cell system or potential, superpotential. So let me describe what's known about these. So there's a complete list of NIMREP graphs. So these are here. So there's the A series, which encode the fusion rules of the categories. Then there's what I'm currently calling the sigma series, conjugate series. So these are infinite families, and then there are 4 exceptionals. Level 8, 2 at level 8, and 2 at level 14. these graphs are actually, in fact, so the graphs on the left are the even parts of thinking diagrams D4k plus 2, E7 and E8, and then the ones on the right are just the odd parts of those graphs. And so this list is complete. It was found a master's student of Terry's had a complete list of symmetric representation graphs for SU3, and so they're the ones that descend to SO3, and then by comparing with modular invariants, which we've classified for SO3, these are the only ones that can remain. On the other hand, the cell system, this work is still ongoing, so uniqueness of the cell system up to some appropriate notion of unitary equivalence is known for the first two graphs on the left, and also this E14C graph at the bottom, so the ones with this sort of triangle is in, whereas the double loop that is in all the other graphs, the double self loop, seems to be leading to a one parameter family of solutions. I believe that they are essentially all equivalent, or maybe that there's at most 4 families of equivalent cell systems, but that currently is still work in progress. But existence is at least known for sigma 2k, so existence at the moment is still unknown for the conjugate E8 and the E14 graphs. Fully expect them to exist. Okay, let me therefore quickly talk about Frobenius algebras for these graphs. So what are some no longer higher rank case of a preprojective algebra, but some perhaps generalized preprojective algebra in a different sense to what Karen was talking about. Following the SU2 sort of situation, it would be tempted to look at this sort of direct sum of all the simple objects, where here Fk is the sum of 2 simple objects. But if you do this is not a Frobenius algebra. It's finite dimensional, but it's not a Frobenius algebra. We also expect, so this is not Frobenius. In analogy, at least to the SU2 and SU3 situations, one would expect that applying the functor f, which is defined in the same way for SU2, SU3, this thing, the algebra you get should be isomorphic to the quotients of the path algebra by an ideal, which, so J should be the ideal generated by the images of cups of caps and the images of this trivariant vertex in the path algebra of G. So the preprojective case, it was just the preprojective relations were coming from this thing. For the SU3 almost Calabi-Yau algebra case, the relations are coming from this thing. We didn't really have that in the same way, and then for SO3 one has both of these pictures. So the correct thing to take seems to be a slightly bigger algebra. is the sum of all the simples that I had in the category C prime that I wrote down first without the y. So you take A, find this vector f to this thing. So this is a graded algebra. Again, so here f of fj is really the space of essential paths on G of length j. So there's a gradient given by path length, which is just really this index j. And what is this? I mean, this actually, so in the SU2 case, so these FJs, these Jones-Bensel projections, are essentially even Jones-Bensel projections from the SU2 case. So this algebra is really just the even part of the preprojective algebra for SU2. So I didn't give that construction. Here I jumped straight to this trivalent picture, but there's a construction of natural homomorphisms from this SO3 picture to the SO2 picture. So this is just the even subalgebra of the preprojective algebra. So the Nakayama automorphism in this case just descends from the Nakayama automorphism of the preprojective algebra, and in fact these graphs G are the ones, they come from the Dynkin diagrams for whom the Nakayama automorphism was trivial. These are precisely the even and odd parts of the Dynkin diagrams for whom the Nakayama automorphism so these are the ones that extend, if you like, to SO3 when you take this quotient by the center. So let me just write out, show. Okay, so as I quickly sketch for SU2, one gets a finite resolution of this algebra as A as left A modules, which again just comes from the fusion rules for SO3. So the only difference now, one from the fusion rules, one gets two. So one gets this exact sequence from the fusion rules just as before, but one can also get a slightly different exact sequence where I've now shifted down, so m has gone to n minus 1. So this is now only valid for m between 2 and 2k, and when you combine these two exact sequences, you get this exact sequence, which is at least for these values of m between 2 and 2k minus 1 is what is given by this resolution. And so from this, hopefully one can construct the resolution of A as A bimodules that will be periodic. One will be able to find a projective resolution which will be periodic, and then from that construct the homology in this case. I think I'm at time.
Any questions, comments? Doesn't seem to be, so maybe we'd like tea or coffee. Thanks very much for that.